Now let's talk about another convention of rotation. In this case, it's called ZYX Euler angles. Okay, what we covered earlier was XYZ fixed angles. This one here is ZYX Euler angles. Okay, so what this represents is the consecutive rotations are made relative to the axes of the frame being rotated. Okay, if you recall, the XYZ fixed angles, we were always rotating about the original frame, the fixed frame. In the case of Euler angles, what we're covering here, we are always rotating about the new frame. Every time we rotate the frame, the new rotation that's coming up would be rotating about axes of the new frame. And then again, the next rotation would be rotation about axis of the new frame. Okay, so that's the big difference between Euler angle rotations and fixed angle rotations. Now, if you look at this, the way we start with this, we start with B coincident with frame A, and then we perform a yaw rotation, which is rotation about Z by the amount of alpha, and then afterwards we perform a pitch rotation, which is rotation about Y by angle beta, and then from there we do a third rotation, which is a roll, which is rotation about X by the amount of gamma. Okay, and after these three rotations, the resultant rotation here, the resultant frame becomes my B frame. All right. Now for this kind of rotation, all the rotations are about the new resulting frame due to the previous rotation. And the result gives the new moved frame, which is frame B. All right, so make sure that you understand this and remember this. The rotations here are about the rotated axes from the previous rotation. Now let's look at this graphically. If I start my frame B and frame A coincident, and then my first rotation here is rotation about Z by alpha. Okay, so since ZA and ZB are the same, once I do the rotation about Z by alpha, then XB and YB will be rotated or deviated away from XA. So I'm going to call this B prime, XB prime and YB prime. And the reason for this is we are not at B yet, so this is only an intermediate step. Now the next step is I'm going to do rotation about Y. Which Y? Remember, in the fixed angles, we did the rotation about the original Y. In here, we're going to do the rotation about the new Y. This is the new Y, the one you see in blue. Okay, it's the YB prime. So when we do the rotation about the new Y, we're gonna move to some new location here for ZB and XB double prime. Okay, so they're gonna move, which is what you see here in the blue line. The blue line is from here, and then once I move and do the second rotation about Y of the new resulting frame by beta, then I will get this green frame. Okay, so that's my second rotation of about Y by beta. Then my third rotation, again, if you look here, that green frame is from here. The new rotation I do about x-axis, x of the new frame, which is the frame here that was green. Okay, so this is my new x-axis. I do the rotation about the new x-axis by the amount of alpha, and that would give me the red axis that you see here, which is frame B. Okay, so this would be my last rotation, which represents frame B. Okay, so all of these rotations happened about the axis, the new axes that are resulting from the previous rotations. Now let's find the equivalent rotation matrix for this Euler convention. The order of matrix multiplication must be the same as the order of rotation as follows. Okay, so if you have the rotation that happens first about Z, then about Y, then about X, then the corresponding rotation matrices are multiplied in the same order. Okay, so if you look at this is rotation about Z by alpha and Y by beta and then X by gamma. Okay, in that sequence, Z, then Y, then X. And that describes frame B relative to A after doing the three rotations. Okay, so when we do the multiplication of the corresponding rotation matrices here, we do the exact same order of multiplication as the order of rotation. So here we have z, then y, then x, then we multiply rotation about z first, then rotation about y, then rotation about x. So now that we have this pointed out here, we already now know the the general form of rotation about z by alpha, so we put it here. And then the rotation about y by beta, again we know the form, so we put it here. And then rotation about x by gamma, again we know the form, so we put it here. If we multiply these three matrices together, then we can come up with the equivalent rotation matrix. If you look here, all the variables here are the three independent variables, which are alpha, beta, and gamma. All 9 elements of this rotation matrix are functions of alpha or beta or gamma, or a combination of these variables. Okay? Now I have a note here. The resultant rotation matrix above is the same as the resultant rotation matrix for the fixed angles when the order of rotation is the opposite. So if you recall, this form here of equivalent rotation matrix looks exactly the same as the form for the equivalent rotation matrix when we had the fixed angles in the previous method. Okay, and if you notice the difference there, we had the fixed angles were in a sequence of rotation about x first and then y and then z. But here in Euler angles, we have rotation about z first and then y and then x. So we rotated here the opposite way that we rotated in the fixed angles case. All right, and that's why when we came here and multiplied the rotation matrices together, it turns out that the rotation matrices were multiplied the same sequence. Since in this case here, we keep the same sequence as the sequence of rotations. And in the fixed angles, we do the opposite sequence as the sequence of rotation. And since we have the opposite sequence of rotation, we have the same rotation matrices that we have right here. Now, I want to emphasize on something here and clarify. Whenever we use the Euler angles, okay, it doesn't matter how many rotations we make and in what order or what sequence. Let's say, for example, we do Euler angle rotation in this method, but we do rotation first about y, then about x, then about z, then about y again, then about z again. It doesn't matter for how many rotations we keep going. As long as we're doing Euler angle convention, we always know that when we try to find the resultant rotation matrix after all these rotations, we always have to multiply the corresponding rotation matrices in the same sequence as the sequence of rotation. Okay, that's Euler angles. Now, if we go back to fixed angles that we covered in the previous topic, if we have a sequence of rotation, again, doesn't matter how many rotations or in what sequence. If we have, for example, rotation first about y, then about z, then about y again, then about x, you know, for however many rotations that you have, what's important to recall that is if you have these rotations happening in the fixed angle convention, which is the previous method, you always have to make sure that when you go and try to multiply these corresponding rotation matrices to find the equivalent rotation matrix, the order of multiplication has always to be the opposite of the order of rotation. Okay, so Euler angles, order of rotations is the same as order of multiplication of rotation matrices. Fixed angles, which is the previous topic, the order of multiplying the corresponding rotation matrices is the opposite of the order of rotations. Okay, so keeping this in mind, now it doesn't matter how many rotations you make. When it's Euler, you know what to do, and when it's fixed angles, you know what to do in terms of the sequence of rotation. Now for Euler angles, what if we have the opposite problem? If we need to find the rotation angles from a rotation matrix, so if we are given the resultant rotation matrix and we are asked to find the alpha, beta, and gamma that represent that rotation matrix, okay? So the rotation matrix is given as rotation about z first by alpha, and then y by beta, and then x by gamma. So if this is given here in general, and we are asked to find gamma and beta and alpha that represent this rotation matrix that was given. as we did earlier in the fixed angles method, we can compare 9 elements, or some of the 9 elements from the given rotation matrix, compare that to the general form of the rotation matrix that we found in the previous step. Okay, and then from these here we can find relationships that would be forming equations of which that if we solve, then we can solve for beta and alpha and gamma. So if we solve these equations, then we can find the general form that define beta and alpha and gamma in terms of the elements of the given rotation matrix. Now, if you guys notice that this general rotation matrix is the exact same rotation matrix that we found for the fixed angles, and since we have already solved for alpha and beta and gamma for that method, for the exact same matrix, then we can just use the same definitions of alpha and beta and gamma in terms of rotation matrix elements. Okay, so since the rotation matrix is the same as that in the fixed angles case, then the values for the 3 angles will be the same as that for this case. All right. So similar to what we did in the previous method here, from R11 and R21 and R31. So this is R11 and this is R21 and this is R31. From these 3 equations that we form from these and these R11, R21, R31, this equals to this and this equals to this and that R31 equals to this. We can find beta equals to a tan 2 of negative R31 and square root of R11 squared plus R21 squared. So the same equation that we found from the previous method when we had fixed angles method. Okay, and then similarly using R11, R21 and beta that we found here, we can find alpha to be a tan 2 of R21 divided by cosine beta and R11 divided by cosine beta. Okay, and then similarly again from R32 and R33 and beta, we can find the value for gamma, which is a tan 2 of R32 divided by cosine beta and R33 divided by cosine beta. And then again we have the same special cases here. When beta equals to positive or negative 90 degrees, then cosine beta would be 0, which means that the denominator in these values here, both this and this, would be 0, and that would be division by 0, which basically makes my equations here non-usable. So in that case, if beta equals to positive 90 degrees, then alpha is always 0 and gamma is a tan 2 of R12 and R22. And when beta is negative 90 degrees, then alpha is always 0 again, and gamma would be negative a tan 2 of R11 and R22. And then note here again, a tan 2 is a function that's used as the arctangent defined using 2 inputs, and this is a function that's already defined in MATLAB. Now let's take an example on Euler angles. Frame B was initially coincident with frame A. We then rotated B about ZB axis by 60 degrees. Then we rotated the new frame about its y-axis by 45 degrees. And this is the keyword that I would like you to pay attention to. The second rotation happened here about the new frame that resulted from the previous rotation. Okay, so that means we're rotating about the new frame, which means we're using Euler angle convention or method. Okay, so that second rotation about y-axis by 45 degrees. Then again, we rotated about the new frame. We rotated the new frame about its x-axis by 30 degrees. Okay, again, we do the rotation about the new axes that are resulting from the previous rotation. Note that the axes of rotation are the new axes resulting from the previous rotation. Now what you need to do is calculate the resultant rotation matrix R of B relative to A. Okay? Now to start solving this problem, I can just go ahead and put my 3 rotations that I already know how to write and define. So rotation about x by 30 degrees, it's given here already. Rotation about x by 30 degrees, so this is the form I put it in. And then the rotation about y by 45 degrees, so I can write it here. And we also have rotation about z by 60 degrees, so I can write it here. Okay. Now, since we are doing rotations about the new axes from the previous rotations, that means we're doing Euler angles, which means that the resultant rotation matrix will be the results of multiplying these individual rotation matrices in the same sequence as the sequence of rotation. So let's see what's the sequence of rotation here. We did rotation about z first, and then about y, and then about x. Okay? So rotation about z by 60 degrees, and then y by 45 degrees, and x by 30 degrees. Okay? Since it's Euler angle method, then we have to keep the same sequence of rotation and do it for the sequence of multiplication of these matrices. So Rz, and then Ry, and then Rx, which matches the rotation about z first, and then y, and then x. Okay? If we substitute these matrices in here, then we can find our equivalent rotation matrix, which comes out to this this rotation, 9 elements of rotations here. Now let's take an in-class exercise here, and I want you to please do this on your own before looking at the answer. Frame B was initially coincident with frame A. We then rotated frame B about XB axis by 30 degrees. Then we rotated the new frame about its y-axis by 45 degrees. Please pay attention. We rotated the new frame about its y-axis. Okay. Then we rotated the new frame about its z-axis by 60 degrees. So again, pay attention to this here. We rotated the new frame about its z-axis by 60 degrees. Calculate the resultant rotation matrix R of B relative to A. Okay. So I want you to solve this on your own. I'm going to pause for a few seconds. Please pause this video and solve this exercise. Once you're done solving this exercise, then you can resume the video and see the answer to the exercise. Okay, now I'm going to assume that you have done the solution here for this exercise, and I'm going to go ahead and show you the answer. So here we have the definition of rotations about x by 30 degrees and y by 45 degrees and z by 60 degrees. We can construct these rotations easily from the given information. And then here we are solving rotation about x first, and then y, and then z by these angles. Since it's Euler angles and it's rotation about the new frames every time, then we are using the same sequence of rotation as the sequence of multiplication of these matrices. Okay, so we're going to do rotation about x, so that means Rx first, and then y, that means Ry second, and then z, that means Rz third. Okay, if you substitute these rotation matrices here, then you get the resultant rotation matrix as shown in here. Please make sure that this matches your solution. If it doesn't match, then go back and see what you did wrong in the multiplication. Now let's take another example here with the opposite problem. Find the z, y, x Euler angles of rotation, alpha, beta, and gamma for the following rotation matrix. So we're given a rotation matrix, which is a resultant rotation matrix after 3 rotations. Rotation about z first, and then y, and then x in the Euler angle convention. And we need to find alpha and beta and gamma that correspond to this resultant rotation matrix. Okay, so as a solution, we already have the equations for each one of these alpha, beta, and gamma in terms of the elements of the given rotation matrix. So for beta, it's equals to a tan 2 of negative R31 and square root of R11 square plus R21 square. I have all these elements here in my rotation matrix that's given. R31 is this element, so I need the negative of R31, which is negative of this negative number, and I'll take this and place it right here, which makes it positive. And then I need the square root here of R11 square. This is my R11, so I take it and place it here. And then R21 square, this is my R21 square, so I take it and place it here. If I evaluate this, then I'll find out that beta equals to 0.2681 or 2618 radians, which is about 15 degrees. Now for alpha, the equation for alpha we found is a tan 2 of R21 divided by cosine beta and R11 divided by cosine beta. I already know R21 from here. This is R21, so I can place it here. And cosine beta, I already found beta to be 15, so I put here cosine 15. And then R11, I already know it from the rotation matrix that given here. And I take this and place it in here. And again, cosine beta is a cosine 15, so I place it right here. If I solve this, then my alpha would be 0.3491 radians, which is 20 degrees that we see here. Now for gamma, the equation for it is a tan 2 of R32 divided by cosine beta and R33 divided by cosine beta. I already know R32. This is my R32. 32, no, I'm sorry. This is my R32 here. Okay, so I take this and I place it right here and divide this by cosine beta. I already found beta to be 15, so I put here cosine 15. And then R33, I already know it here. This is my R33. So I place it here and I divide it by cosine beta, which is cosine 15. If I solve this, I'm going to find alpha to be 0.1745 radians, which is 10 degrees. Now I wanted to check at home for the ZYX order of rotation. Can you find the same rotation of B relative to A that was given here? By multiplying each of the rotation matrices in the following order. So we already found these angles, so if you put it in the same order, RZ of 20 degrees times RY of 15 degrees times Rx of 10 degrees. If you do this order of multiplication, which represents Euler angle, the same order of rotation for Euler angle convention, would that give you RBA back? So please check and make sure that we get R of B relative to A as given here. Now let's take an in-class exercise here. Find the ZYX Euler angles of rotation, alpha, beta, and gamma for the following rotation matrix. And the rotation matrix is given here, rotation of B relative to A. I want you to solve this on your own, so I'm going to pause for a few seconds. Please pause this video. Once you're done with this exercise, then you can resume the video and see the answer to this exercise. Okay, now I'm going to assume that you are done with solving this exercise. I'm going to go ahead and start showing the solution. So for beta, the definition of beta is a tan 2 of negative R31 and square root of R11 squared plus R21 squared. So R31 is given here to be negative 0.5. Negative of that negative would be positive 0.5. I can put here. And then R11 is this R, first row, first column, 0.6124. So I can put it here. And then R21 is R of the second row, first column, which is 0.6124, which I can put right here. If you solve this, you're going to find out that beta equals to 0.5236 radians or 30 degrees. Okay? So that solves beta. We go on to alpha, which is a tan 2 of R21 divided by cosine beta and R11 divided by cosine beta. R21 is R of the second row, first column, which is right here. And we can put this in here. And then cosine beta, we already found beta to be 30 degrees, so we can put here cosine of 30 degrees. And then R11 is right here, first row, first column, so I can place it here and divide it by cosine beta, which is cosine 30 degrees right here. If I solve this, I'm going to find out that alpha equals to 0.7854 radians or 45 degrees. Okay, for gamma now, a tan 2 of R32 divided by cosine beta and R33 divided by cosine beta. R32 is R of the third row, second column, right here, 0.75. So I can take this and put it here and divide this by cosine beta, which is cosine of 30 degrees. And I can place it right here. And then R33 is R of the third row, third column, 0.433. And I can place it here and divide that by cosine beta, which is cosine 30 degrees. If I solve this, I'm going to find out that gamma equals to 1.0427 radians or 60 degrees. Okay, so that's the solution for this exercise, where we found alpha, beta, and gamma angles that correspond to this equivalent rotation matrix.